Hello, my name is Thais Arslanbekov, and this is my lab report about charged tapes for Physics 2212. The key ideas of this lab are Coulomb's law, which describes the electric force between two charged particles as a function of the distance between them, with both particles having a charge. The electric field is a force created by a charged particle, or basically a force a small charged particle would feel when it is a certain distance apart from another charged particle. If two charges are opposite in signs, they will attract, but if they have the same charge, they will repel. This lab also concerns gravitational force, which is the force of attraction of an object to Earth's surface due to its mass. Similarly, vectors are utilized in this lab, which have magnitude and direction. The models and fundamental principles of this lab are the aforementioned Coulomb's laws and electric field. For our purposes, the surroundings is tape A and the rest of the universe, and the system is considered tape B. Coulomb's law quantifies the electric force between two charged particles as the product of their magnitudes multiplied by k and divided by the squared distance between them. Gravitational force is equal to the mass of an object multiplied by g, or 9.81 meters per second squared. My predictions are based on the fact that opposite charges attract and like charges repel, so tape B will be repelled from tape A because of the same charge. Tape B is negatively charged because it was repelled when brought close to a negatively charged pen. Here's an excerpt from the code, and the entire computational model is linked in the description. The electric force function is defined as a function of the charges and the distance between them, and based on the free diagram provided in the next slides, the gravitational force is equal in magnitude but opposite in direction to the electric force. The electrical field created by tape B is equal to the force divided by the charge of B. Note that the charges of A and B are employed as equal, since the charges were generated in the same manner, so it is safe to assume that they are equal. Notice that the electric force on tape B due to tape A is opposite in direction to the gravitational force of B, as aforementioned. Tape B is negatively charged, with a charge of approximately negative 2.25 times 10 to the negative 9 coulombs. The electric field at tape B due to tape A is approximately 810,000 newtons per coulomb. If a U-tip is positively charged, it would attract a negatively charged pen, since they are opposite charges. If it was negatively charged, they would repel, since they are like charges. All charged objects attract neutral objects, so they would attract. The net y component is 0 because the vertical gravitational and electrical forces are balanced, since tape B is in equilibrium in the y-axis. Vertical forces are exerted by the Earth, the gravitational force down, and by tape A, the electrical force upwards, and these two forces are balanced as aforementioned. One needs to measure the mass of tape B to determine the gravitational force on it. Here are my experimental values. For the separation distance, I calculated that it was 0.005 meters. The mass of tape B was 1.86 times 10 to the negative 4 kilograms. The length of tape B was 18.6 centimeters, or 0.186 meters, and the width of tape B was 0.017 meters. The gravitational force of tape B is given by the equation F of gravity equals mg, which is 1.86 times 10 to the negative 4 kilograms times 9.81 meters per second squared, which gives a value of 0.00182 newtons. By the free body diagram provided a couple slides ago, the magnitudes of the gravitational force and the electric force are equal. So therefore we can set up an equation to find the magnitude of the charge on tape B, which would be 2.25 times 10 to the negative 9 coulombs. In order to find the electron deficiency of tape B, we have to first find the area of the tape, which is given by multiplying its width times its length, giving us 0.003162 meters squared. And then we assume that the area of one atom is about 10 to the negative 20 meters squared. Therefore, the number of atoms is given by the area of the tape over the area of one atom. So there are approximately 3.162 times 10 to the 17th atoms. And the number of electrons is given by the charge that we found to be 2.25 times 10 to the negative 9 coulombs divided by the elementary charge, which is 1.6 times 10 to the negative 19 coulombs, which gives us 1.406 times 10 to the 10th electrons. And the ratio of the number of electrons to the number of atoms, it's 4.446 times 10 to the negative 8th. And in these calculations, we are assuming that the tape is exactly one atom thick, which obviously is not the case in real life. Here are the results of the computational model, which coincide with the calculations performed by hand, and the magnitude of the charge of the tape based on the computational model, it is also 2.25 times 10 to the negative 9 coulombs. There is no reason in ignoring air resistance in a moving object for this lab because tape B is static in static equilibrium, so therefore it is irrelevant, and we are treating the long tape as a point charge because this is the assumption we need to make in order to calculate the force between the two charges and in order to find the electric field on B by A. And we are also assuming that each tape has the same amount of charge with even distribution, which allows us to utilize Coulomb's law. If electrons and protons had switched charges, this would not affect our model whatsoever, because this just changes the convention of the model and not real life, so it would not change any of the observations, as the opposite charges would still attract and the like charges would still repel. And it's important to minimally handle charged tapes because physical contact can allow for a flow of electrons onto the surface that touches the tape, so excess electrons forming the charge can escape onto the surface, which would effectively decrease the magnitude of the charge on tape and therefore also the separation distance. So minimally touching the charged tapes allows them to retain their charge better. Thank you so much, and I hope you have a great rest of your day.